Look up at the night sky. What do you see? A scattering of stars, maybe a planet or two, the faint glow of the Milky Way stretching across the darkness. It feels familiar, almost comforting, but beyond that quiet beauty lies a universe teeming with structures so bizarre, so utterly perplexing, they challenge everything we think we know about space. Galactic formations that defy physics, cosmic mysteries that leave even the brightest scientists scratching their heads. And today, we're diving deep into 25 of the most mind-bending enigmas the universe has to offer. Picture a place where stars orbit an invisible point in space, where galaxies arrange themselves in perfect geometric patterns, where entire regions of the cosmos glow with no discernible source of light. These aren't scenes from science fiction, they're real, documented phenomena, hiding in plain sight within the vast expanse of the universe. Some of these structures are so large, they shouldn't exist according to our current understanding of physics. Others behave in ways that seem to rewrite the rules of reality itself, and the deeper we look, the more questions they raise. What forces could possibly create something so strange? Are we missing a fundamental piece of the cosmic puzzle? This journey isn't just about listing oddities, it's about stepping into the unknown, where every discovery peels back another layer of the universe's secrets. From colossal rings of galaxies spanning billions of light years to eerie voids where nothing seems to exist, these cosmic wonders aren't just fascinating, they're clues pointing toward truths we're only beginning to grasp. So buckle up, by the time we're done, you'll never look at the night sky the same way again. The Hercules-Corona Borealis Great Wall isn't just big, it's unthinkably vast. Stretching an astonishing 10 billion light-years across, this cosmic megastructure holds the title as the largest single entity we've ever discovered in the observable universe. To put that into perspective, if you could travel at the speed of light, it would take you longer to cross this wall than the current age of our entire planet. And yet, there it sits, a sprawling filament of galaxies clustered together in a pattern so immense, it shouldn't exist, at least, not according to our current understanding of how the cosmos works. Scientists first stumbled upon this behemoth in 2013, while mapping gamma-ray bursts, the violent explosions marking the deaths of massive stars. These bursts acted like cosmic breadcrumbs, revealing an eerie concentration of galaxies forming a structure far larger than anyone thought possible. The discovery sent shockwaves through the astronomy community because it directly challenges one of cosmology's bedrock ideas, the cosmological principle. This principle states that, on a large enough scale, the universe should look roughly the same no matter where you are. Matter should be evenly distributed, like raisins scattered through a loaf of bread. But the Hercules-Corona Borealis Great Wall, it's more like finding a single gargantuan raisin the size of the entire oven. What makes this structure so baffling isn't just its size, it's when it exists. The universe is only about 13.8 billion years old, yet here we're seeing something that spans nearly 3/4 of that timeline. How could gravity have pulled matter together on such a colossal scale so quickly after the Big Bang? It's like watching a city spring up overnight in a barren desert, except this city is made of galaxies, and the overnight spans billions of years. Some theorists suggest we might need entirely new physics to explain it, while others wonder if we're simply seeing a statistical fluke, a trick of perspective. But with every new observation, the Great Wall only grows more enigmatic, forcing us to question whether we truly understand the universe's architecture, or if we're just glimpsing the edge of something far stranger. But if you thought the Hercules-Corona Borealis Great Wall stretched the limits of what we thought possible, wait until you hear about the giant arc, a cosmic curveball that's rewriting the rules of galactic architecture. Picture this, a graceful, crescent-shaped chain of galaxies spanning an almost inconceivable 3.3 billion light-years, dangling across the universe like a shimmering necklace. At first glance, it's breathtaking, but when astronomers peer closer, they realize something's deeply wrong. This structure shouldn't exist. The giant arc was discovered in 2021 by a team analyzing the light from distant quasars, using it to map the distribution of galaxies in a slice of the universe roughly 9 billion light-years away. What they found wasn't just surprising, it was impossible. According to our best models of large-scale structure formation, matter in the universe should clump together in a more or less random, web-like pattern, with filaments and voids forming organically over billions of years. But the giant arc, it's too symmetrical, too perfectly curved, as if some unseen hand sculpted it. This precision throws dark matter, the invisible glue thought to hold galaxies together, into question. If dark matter's gravitational pull is responsible for shaping the universe, why would it create something so unnaturally balanced? Some researchers argue the arc might be a statistical fluke, a trick of perspective where unrelated galaxies appear aligned from our viewpoint. But the odds of that are astronomically low, like rolling a die 100 times and getting the same number every single time. Others suggest we might be seeing evidence of exotic physics, forces or interactions we haven't even discovered yet. What's truly mind-bending is the timing. The giant arc existed when the universe was only about half its current age, a period when cosmic structures were still in their infancy. How did something so vast and coherent assemble so quickly? It's like finding a fully formed skyscraper in the middle of a construction site where only foundations should exist. Every new observation deepens the mystery, leaving astronomers with more questions than answers. Is the arc a cosmic coincidence, a flaw in our theories, or a signpost pointing toward an entirely new understanding of the universe? One thing's certain, the more we uncover, the clearer it becomes that the cosmos loves to defy expectations. Hoag's object isn't just a galaxy, it's a cosmic riddle wrapped in a ring of starlight. Floating some 600 million light-years away, this celestial oddity looks like something an artist dreamed up. A perfectly round, golden core of ancient stars, encircled by a shimmering blue loop so precise it could have been drawn with a compass. Most galaxies come in spirals or blobs, but Hoag's object defies categorization, standing alone as one of the rarest structures in the universe, and for decades, its very existence has left astronomers utterly stumped. The mystery begins with that uncanny symmetry. The inner core measures about 24,000 light-years across, packed tightly with aging stars that glow a warm yellow. Then, like a halo frozen in space, a near-perfect ring of younger, hotter blue stars orbits at a crisp distance 75,000 light-years from edge to edge. Between them, almost nothing. A yawning gap of near-total darkness separates the two stellar populations, as if someone took a cosmic eraser and scrubbed away any trace of stars bridging the divide. This bizarre structure isn't just unusual, it's unprecedented. Of the billions of galaxies we've observed, fewer than 0.1% share this ringed configuration, and none match Hoag's object's eerie precision. So how does something like this form? The leading theory points to a cataclysmic collision, a smaller galaxy plowing through the heart of Hoag's object billions of years ago, sending shockwaves rippling through its gas clouds. Those waves could have compressed material into a dense ring, triggering a fireworks show of star formation at the edges while leaving the core untouched. But there's a problem. No evidence of chaos remains, no distorted trails of stars, no leftover debris from an intruder galaxy, just that pristine, symmetrical divide. It's like finding a shattered vase reassembled with no glue or cracks, as if the pieces simply knew where to fall back into place. Another idea suggests resonant star formation, where gravitational instabilities in the galaxy's disk create waves that shepherd gas into a perfect ring. Think of it like dropping pebbles into a pond. The ripples align just right, concentrating star birth along the crests, but even this explanation strains credulity. Resonances usually produce multiple rings or spirals, not a single isolated loop floating in empty space. And why hasn't the ring scattered or blurred over billions of years? The more we study Hoag's object, the clearer it becomes. This isn't just a fluke. It's a glimpse into a process we don't fully understand. A cosmic ballet where gravity, time, and chance conspire to create something achingly beautiful and utterly inexplicable. What truly haunts researchers is the possibility that Hoag's object might not be alone. Recent surveys have spotted other ringed galaxies with similar gaps, hinting at an entire family of these outliers hiding in plain sight. Could they all form the same way, or is each one a unique accident of physics? Every answer peels back another layer of mystery, reminding us that the universe has a flair for the unexpected. After all, if something as strange as Hoag's object can exist, what else is out there waiting to rewrite the rules? Most of us picture the universe as a bustling cosmic metropolis, galaxies clustered together, stars twinkling in every direction. But what if I told you there are places so empty, so profoundly hollow, that stumbling into one would feel like being the only person in a country the size of the United States? Enter the Bootes void and the Eridanus supervoid, two of the most unsettling holes in the fabric of space, where nothingness isn't just an absence, it's a glaring anomaly that challenges our understanding of reality itself. The Bootes void, nicknamed the Great Nothing, is a spherical chasm spanning a staggering 330 million light-years. To grasp how desolate this region is, consider this. If you placed our Milky Way at its center, you'd need to travel the equivalent of 10,000 Milky Ways end to end before encountering another galaxy. Normally, a space this vast should contain at least 2,000 galaxies, but the Bootes void, astronomers have found fewer than 60. It's as if someone took a cosmic vacuum and sucked away nearly everything, leaving behind a ghostly pocket of near-perfect emptiness. So how does something like this form? The leading theory suggests smaller voids common throughout the universe might have merged over billions of years, like soap bubbles combining into one giant bubble. But even that doesn't fully explain the Bootes void's extreme scale. Some researchers speculated could be evidence of an ancient collision with a parallel universe, a crack in space-time where matter was somehow erased. Others argue it's a statistical fluke, a rare but natural gap in the cosmic web. Yet every time we point telescopes at it, the void stares back, silent and defiant, refusing to give up its secrets. Then there's the Eridanus supervoid, a different kind of cosmic enigma. Unlike the Bootes void's pure emptiness, this 3 billion light-year wide region is infamous for what it doesn't do: glow. Nestled within it is the CMB cold spot, a mysterious patch of the universe's afterglow, the cosmic microwave background that's colder than it should be. Imagine the Big Bang's echo, a fading warmth permeating all of space, except here where the temperature drops inexplicably. At first, scientists thought the cold spot might be a measurement error. But repeated observations confirmed it's real, and the Eridanus supervoid seems to be the culprit. As light travels through a void, it loses energy climbing out of the gravitational well, a phenomenon called the integrated Sachs-Wolf effect. The supervoid's sheer size could theoretically explain the temperature dip, except there's a catch. The cold spot is too cold, too large. Even this void shouldn't create such an extreme anomaly. Some theorists propose an even wilder explanation. The cold spot might be a bruise left by a collision with another universe during cosmic inflation, a time when the fabric of reality expanded faster than light. Others wonder if dark energy, the force accelerating the universe's expansion, behaves differently in these voids, warping space in ways we don't yet understand. What makes these voids so unnerving isn't just their emptiness, it's what they imply. If the universe is truly uniform, as the cosmological principle insists, why do these staggering deserts exist? Are they mere outliers, or do they hint at flaws in our fundamental models? Every unanswered question peels back another layer of our cosmic ignorance, reminding us that even nothingness can be full of secrets. Rising from the heart of our galaxy like twin cosmic geysers, the Fermi bubbles are a pair of colossal, ghostly structures that stretch 25,000 light-years above and below the Milky Way's disk. Discovered in 2010 by NASA, a Fermi gamma-ray space telescope, these towering formations glow with high-energy gamma radiation, painting a picture of violence on a scale we're only beginning to comprehend. What's astonishing isn't just their size, enough to engulf half our night sky if we could see them, but the fact that they've been hiding in plain sight, invisible to human eyes until modern telescopes peeled back the curtain. The bubble's discovery was pure serendipity. Astronomers were mapping gamma-ray sources across the sky when they noticed an unexpected haze stretching from the constellation Virgo down to Grus, like an hourglass etched into the fabric of space. Further observations revealed these weren't random emissions, they were the edges of two symmetrical lobes, each pumping out energy equivalent to 100,000 exploding stars. The implications were staggering. Our galaxy's core had erupted at some point in the past, and whatever happened there left scars we're just now deciphering. So what could unleash such fury? The prime suspect is Sagittarius A, the supermassive black hole squatting at the Milky Way center. Normally, it's a quiet beast, but simulations suggest it might have gone through a frenzied feeding spree 6 million years ago, devouring a colossal cloud of gas. As matter spiraled into the black hole's maw, it could have triggered twin jets of charged particles, blasting outward at nearly the speed of light and inflating these gamma-ray balloons. Think of it like a pressure cooker exploding, except this one is 4 million times the mass of our Sun, and its steam is enough to cook entire galaxies. But there's a twist. Some researchers argue the bubbles are too perfect, too symmetrical for a messy black hole outburst. Their crisp edges and uniform energy distribution hint at something even stranger: dark matter annihilation. If hypothetical dark matter particles collided and destroyed each other near the galactic center, the resulting energy could have sculpted these pristine structures. It's a tantalizing idea, proof that dark matter isn't just an invisible scaffold for the universe, but an active participant in its most dramatic events. Yet despite a decade of study, the Fermi bubbles refuse to give up their secrets. Their gamma rays don't match any known particle interactions perfectly, and their sheer size suggests the eruption, if that's what it was, lasted far longer than any black hole outburst we've seen elsewhere. Even stranger, recent data shows the bubbles might be older than we thought, their roots possibly intertwined with another mystery: the Milky Way's X-ray chimneys, vast tunnels of hot gas funneling energy from the core. Are these features separate events or pieces of a single, catastrophic galactic tantrum? The more we learn, the clearer it becomes. The Fermi bubbles aren't just relics. They're a live wire, a testament to the fact that even our home galaxy, seemingly calm and familiar, has a volatile past we're only beginning to unravel. And if something this dramatic happened once, what's stopping it from happening again? Right now, Andromeda, our closest galactic neighbor, is hurtling toward the Milky Way at 250,000 miles per hour. It might sound like the plot of a cosmic disaster movie, but this isn't science fiction. In about 4 billion years, these two spiral giants will slam into each other, triggering a gravitational dance so chaotic, so spectacular, it'll rewrite the night sky forever. And believe it or not, the collision has already begun. Telescopes have spotted the first whispers of this inevitable merger. Vast streams of stars, gas, and dark matter stretching between the galaxies like cosmic taffy, pulled loose by gravity's relentless tug. These tidal tales are the universe's earliest warning signs, evidence that Andromeda and the Milky Way aren't just neighbors. They're already touching, their outermost halos brushing against each other in a slow-motion preview of the cataclysm to come. Imagine two swimmers circling a pool, each trailing ripples that start to overlap long before they collide. That's what's happening here, except the swimmers are galaxies, and their ripples are stars being flung into the void. Simulations of the merger reveal a spectacle beyond anything human eyes will witness. As Andromeda's gravity distorts the Milky Way's spiral arms, our familiar night sky will warp into something unrecognizable. Stars won't just twinkle, they'll streak, hurled into new orbits by gravitational chaos. The two black holes at each galaxy's core, Sagittarius A and Andromeda's even more massive counterpart, will spiral toward each other, shredding nearby stars and unleashing tsunamis of radiation. And through it all, new stars will ignite in shockwaves of colliding gas, painting the heavens with brilliant blue clusters younger than the dinosaurs are to us. But here's the twist: despite the violence, the merger won't destroy either galaxy. Instead, they'll coalesce into a single, elliptical behemoth dubbed Andromeda over billions of years. Earth, it'll probably survive, flung to some distant orbit, but our solar system's fate hinges on a cosmic roll of the dice. The real casualty will be the Milky Way's iconic spiral shape, erased forever in the tumult. What's fascinating isn't just the scale of this event, it's the timing. Right now, we're witnessing the prelude, a chance to study how galaxies interact before the main act. Those faint tidal streams, they're gold mines for astronomers, revealing how dark matter, the invisible skeleton of the universe, guides the merger. And by observing similar collisions in distant galaxies, we've learned these encounters aren't rare. They're the universe's way of recycling, turning spirals into ellipticals in a cycle as old as time. So while we'll never see Andromeda's birth, its ghostly prologue is unfolding above us tonight. The Milky Way, as we know it, is living on borrowed time, a fleeting masterpiece in an ever-changing cosmos. Somewhere beyond the edge of everything we can see, something massive is pulling. Not just one galaxy or a cluster, but thousands of them, all streaming in the same direction at breakneck speeds, as if the universe itself is tilted. This is the dark flow, one of cosmology's most unsettling mysteries, and it suggests either a revolutionary truth about reality, or that we've been measuring the cosmos all wrong. The story begins in 2008, when astronomers studying the cosmic microwave background, the afterglow of the Big Bang, noticed something peculiar. Galaxy clusters weren't just drifting randomly, they showed a coordinated motion toward a single patch of sky near the constellations Centaurus and Vela, moving at speeds exceeding 2 million miles per hour. That's like every object in a crowded airport suddenly sprinting toward the same exit, ignoring the laws of traffic. And here's the kicker: the source of this pull lies beyond the observable universe, in a region of space so distant, its light hasn't had time to reach us in the 13.8 billion years since the cosmos began. At first, scientists assumed it was a measurement error. After all, the dark flow's proposed explanation sounds like science fiction. A gravitational anomaly from another universe, tugging on ours like a magnet hidden behind a curtain. The idea stems from multiverse theories, where our universe is one bubble among countless others in an infinite cosmic foam. If a neighboring bubble universe collided with ours long ago, the lingering gravitational distortion could theoretically explain this coordinated motion. It's a tantalizing thought, proof that we're not alone in the grand scheme of reality. But critics argue there's a simpler answer: our measurements are flawed. Tracking galaxy clusters at such distances relies on the Sunyaev-Zeldovich effect, where hot gas distorts the cosmic microwave background in predictable ways. If we've misjudged how this effect works at extreme scales, the dark flow could just be an illusion, a cosmic mirage born from incomplete data. Some researchers point to quirks in the Planck satellite's readings, suggesting statistical noise might mimic a false flow. Others propose that superclusters we can see, like the Shapley attractor, might be responsible, their combined gravity tugging more strongly than we'd calculated. Yet the more we study it, the stranger the dark flow gets. Recent surveys found the motion extends even farther than initially thought, billions of light years, with no known structure large enough to explain it. If it's real, it implies the observable universe isn't just a random patch but a fragment of something bigger, like a single tile in a mosaic we can't yet see. That would shatter the cosmological principle, the bedrock idea that the universe is uniform everywhere. So where does that leave us in a race between two possibilities? Either we're standing at the shoreline of a multiverse, catching tides from unseen shores, or our best tools for mapping the cosmos are painting mirages. Both answers would rewrite physics, and until we know for sure, the dark flow remains a ghostly finger pointing toward the unknown, reminding us that even the emptiest corners of space might be hiding secrets we've barely begun to imagine. The Sombrero Galaxy isn't just another pretty face in the cosmic crowd, it's a celestial shapeshifter, blurring the line between two galactic categories in a way that's left astronomers baffled for decades. Officially catalogued as M104, this stunning object floats 28 million light-years away, wearing its signature dust lane like a tilted brim on a cosmic hat. But peer closer and the real magic reveals itself. This galaxy refuses to fit neatly into either the spiral or elliptical family. Instead, it's a stunning hybrid, a cosmic chimera that challenges everything we thought we knew about how galaxies evolve. What makes the Sombrero so perplexing starts with its structure. Most spirals, like our Milky Way, boast graceful arms swirling around a bright central bulge, while ellipticals are featureless blobs of aging stars. The Sombrero, it's got both. A razor-thin disk of gas and dust spins around its equator-classic spiral behavior, yet its core swells into a massive, football-shaped bulge more typical of an elliptical. Even stranger, that iconic dust lane isn't aligned with the galaxy's rotation like it should be. Instead, it's warped, kinked at odd angles as if some invisible hand crumpled it like paper. This isn't just unusual, it's unheard of in normal spiral galaxies, suggesting a turbulent past we're only beginning to unravel. The secret might lie in the galaxy's monstrous heart. Lurking at its center is a supermassive black hole weighing in at 1 billion solar masses, one of the heaviest ever measured. That's 25 times heftier than Sagittarius, a star, the black hole anchoring the Milky Way. Such a behemoth wouldn't just sit quietly, it would dominate its surroundings, stirring the galactic pot with gravitational fury. Some theorists suggest this black hole's violent feeding cycles could explain the Sombrero's dual personality. Imagine a spiral galaxy minding its own business until its central black hole goes on a rampage, devouring nearby stars and gas. The resulting energy might puff up the core into an elliptical-like bulge while leaving the outer disk intact, like a pastry chef who folds butter into dough, creating layers of contrasting texture. But there's another twist. The Sombrero's outer halo is littered with ancient star clusters, far older than anything in its disk. This hints at a dramatic collision billions of years ago, where a smaller galaxy plunged through the Sombrero's heart. The intruder's stars would have scattered into the halo, while its gas settled into the warped disk we see today. It's the cosmic equivalent of throwing a rock into a pond. The ripples freeze into place, leaving a permanent record of the chaos. Yet even this explanation doesn't quite fit. Simulations show mergers usually destroy delicate spiral structures, leaving behind messy ellipticals. So how did the Sombrero preserve its pristine disk? Some researchers propose it underwent a gentle merger where the colliding galaxy was mostly dark matter, leaving the visible disk unscathed. Others wonder if we're seeing a rare transitional phase, a spiral caught mid-transformation into an elliptical, frozen in time like a butterfly halfway out of its cocoon. Every new observation deepens the mystery. Recent infrared images reveal the dust lane isn't just warped, it's braided, twisted into intricate loops that defy simple gravitational explanations. Meanwhile, the galaxy's outer regions rotate backward compared to the inner disk, as if some cosmic hand spun the outer edge like a flipped record. These quirks suggest the sombrero isn't just an oddball, it's a Rosetta Stone for understanding how galaxies defy categorization. What's clear is this: the sombrero galaxy isn't just a pretty picture. It's a living laboratory, a place where the universe experiments with form and function on a scale we're only beginning to comprehend. And as we peel back its layers, we're forced to ask how many other galactic rule breakers are out there, hiding in plain sight. Deep in the heart of the Phoenix Cluster, a cosmic assembly of galaxies some 5.7 billion light-years away, something impossible is happening. This isn't just another cluster, it's a stellar nursery on steroids, churning out an astonishing 740 new stars every year. To put that into perspective, our Milky Way manages 1 or 2 in the same time frame. The Phoenix Cluster isn't just breaking records, it's rewriting the playbook on how galaxies grow. And at the center of it all lies a supermassive black hole doing the exact opposite of what scientists expected. Black holes have a reputation as cosmic killjoys. Their intense gravity and violent outbursts of energy are supposed to prevent star formation by heating up or blowing away the cold gas needed to make new stars. But the Phoenix Cluster's central black hole, it's playing by different rules. Instead of stifling star birth, it's fueling it, creating a feedback loop so bizarre. It's like watching a wildfire generate the water meant to put it out. Here's how it works. At the cluster's core, the black hole feasts on surrounding gas, launching jets of superheated plasma that carve through space at nearly light speed. Normally, these jets would act like cosmic blowtorches, sterilizing entire galaxies. But in the Phoenix Cluster, something extraordinary happens. The jets stall. As they plow into the surrounding gas, they create vast shockwaves that cool the gas instead of heating it, causing it to condense into dense star-forming clouds. It's the universe's ultimate irony. The very energy meant to suppress star birth is enabling it on an unprecedented scale. What makes this even more puzzling is the sheer amount of cool gas involved. The Phoenix Cluster's central galaxy is drowning in it enough to form stars at this breakneck pace for billions of years. That's like finding a reservoir in the middle of a desert, constantly refilling itself despite the scorching sun. Astronomers call this a cooling flow, where gas should be steadily raining down into the galaxy's core. But there's a problem: most clusters don't behave this way. Their central black holes prevent cooling flows by pumping energy back into the system. So why is the Phoenix Cluster different? The answer might lie in its balance or lack thereof. The black hole's outbursts are powerful enough to stir the pot, but not so violent that they completely disrupt the gas. Think of it like a chef simmering a sauce. Too much heat burns it, too little leaves it cold, but just the right amount creates the perfect consistency. In the Phoenix Cluster, this delicate equilibrium allows the gas to cool just enough to form stars without being obliterated. Yet even this explanation doesn't account for the staggering numbers. 740 stars a year isn't just unusual, it's unprecedented in the known universe. Some theorists suggest the cluster might be in a rare, short-lived phase, a cosmic sweet spot where conditions align perfectly for runaway star formation. Others wonder if we're seeing the aftermath of a colossal collision, where a merger between galaxies funneled an unnatural amount of gas into the center. But perhaps the most tantalizing possibility is that the Phoenix Cluster isn't unique just early. In the distant past, when the universe was younger and denser, such extreme star factories might have been common. If so, this cluster is a time capsule, offering a glimpse into an era when galaxies forged stars with reckless abandon, shaping the cosmos as we know it. One thing's certain: the Phoenix Cluster doesn't just defy expectations, it challenges them. In a universe where black holes are supposed to be destroyers, here's one playing creator, sculpting new stars on a scale that borders on the surreal. And as we stare into this cosmic contradiction, we're left with a humbling thought: maybe we've only begun to understand the rules of the game. Most dying stars go out with a bang, supernova that light up the cosmos or planetary nebulae that bloom like celestial flowers. But HD 44179, the aging star at the heart of the Red Rectangle Nebula, chose a different path. Instead of fading into chaos, it sculpted its final act into one of the most geometrically perfect structures ever seen in space, a near-flawless rectangle glowing crimson against the blackness of the universe. This isn't just a cosmic coincidence, it's a precision so rare, so unnatural, that astronomers have spent decades unraveling the physics behind its razor-sharp edges. The red rectangle, floating about 2,300 light-years away in the constellation Monoceros, gets its name from its striking appearance, a nested set of concentric rectangles, like a target painted in shades of ruby and garnet. At its core, two stars orbit each other in a tight dance, their gravitational waltz shaping the nebula's outflow into that impossible symmetry. Most planetary nebulae sprawl in organic, asymmetrical patterns, their gas ejected in erratic bursts. But here, the stars expelled material folds into crisp, angular layers, as if guided by an invisible blueprint. The secret lies in those dueling stars. As the primary star, a post-red giant, sheds its outer layers, its smaller companion star funnels the escaping gas into two opposing cones. These cones, viewed almost edge-on from Earth, create the illusion of an X at the nebula's center, while the star's thick dust ring acts like a stencil, carving the gas into those iconic rectangular shapes. Imagine blowing smoke rings through a keyhole. The geometry of the opening dictates the form the smoke takes. That's essentially what's happening here, but on a cosmic scale, with stellar winds and gravity playing the role of the artist. What's even more fascinating is the nebula's color. The deep red hue comes from a rare type of carbon-based molecules called polycyclic aromatic hydrocarbons, lit up by the central star's ultraviolet light. These molecules shouldn't survive long in the harsh environment of a planetary nebula, yet here they thrive, painting the structure in hues that defy expectations. Some scientists speculate the binary system's unique dynamics might be shielding them, creating pockets where complex chemistry can persist. But the real puzzle: why don't more nebulae look like this? Binary stars aren't uncommon, yet the red rectangle's precision is virtually one of a kind. The answer might hinge on timing and alignment. For the rectangles to form, the dying star's outflow must collide with the companion's gravitational field at just the right angle, with just the right speed. Even a slight deviation would scatter the gas into the usual chaotic swirls we see elsewhere. It's like throwing a pebble into a pond and having the ripples freeze into perfect squares, a fleeting balance of forces that rarely align. The red rectangle isn't just a cosmic oddity, it's a lesson in how delicate the universe's artistry can be. As the central star continues to fade, its once vibrant geometry will eventually dissolve, leaving behind only a white dwarf and the echoes of a structure so precise it feels almost engineered. And that's the most haunting thought of all. If nature can create something this meticulous by chance, what other unimaginable patterns might be hiding in the depths of space? The Whirlpool Galaxy isn't just another pretty spiral, it's a cosmic masterpiece, a whirl of stars and gas so flawless it could have been sketched by an astronomer's dream. Officially known as M51, this face-on spiral floats 23 million light-years away, its arms winding outward in a near-mathematical perfection that's earned it the nickname the Grand Design. But look closer and you'll find this beauty isn't solo. It's locked in a gravitational tango with its smaller, chaotic partner, NGC 5195. Together, they're rewriting the story of how galaxies grow not in isolation, but through violent, star-sparking collisions. What makes the whirlpool so mesmerizing starts with those iconic arms. Unlike many spirals where star-forming regions scatter randomly, M51's arms are lined with nearly surgical precision, each one traced by bright blue clusters of newborn stars and glowing pink hydrogen clouds. This clarity comes from a phenomenon called density waves, gravitational ripples that move through the galaxy's disk like sound waves through air, compressing gas and triggering star formation in their wake. Think of it like traffic on a highway. When cars slow down, they bunch up, creating visible clumps. In the whirlpool, those clumps are stellar nurseries strung along the arms like pearls on a cosmic necklace. But there's a twist to this elegance. None of it would exist without destruction. The whirlpool's flawless spiral is actually the result of a brutal gravitational assault. NGC 5195, its dwarf companion, has been plowing through M51's outskirts for hundreds of millions of years, its gravity yanking on the larger galaxies' gas and dust like a child dragging a stick through wet sand. These tidal forces are what sculpted those textbook-perfect arms, kickstarting the density waves that now define the whirlpool's structure. It's a cosmic irony. The very chaos that should tear a galaxy apart instead shaped it into one of the universe's most photogenic wonders. The proof is in the details. Infrared and radio observations reveal filaments of gas stretching between the two galaxies, evidence of material being torn loose in their gravitational tug-of-war. And nestled along the whirlpool's arms are knots of star formation superstar clusters blazing with the light of millions of young suns, all born from the shockwaves of this ongoing collision. Some of these clusters are so dense they might one day become globular clusters, the ancient stellar cities that orbit galaxies like relics of their violent past. Yet for all the violence, there's an odd harmony here. NGC 5195 isn't just a disruptor, it's a catalyst. As it tugs at the whirlpool, it funnels fresh gas into the larger galaxy's core, fueling its supermassive black hole and extending the spiral's star-forming lifespan. Without this turbulent partnership, M51 might have exhausted its gas eons ago, fading into a quiet, aging disk. Instead, it's thriving, a testament to how even the most destructive forces in the universe can birth extraordinary beauty. The whirlpool's dance isn't just a spectacle, it's a window into our own future. In about 4 billion years, the Milky Way will collide with Andromeda in a similar slow-motion merger. Will our galaxy's spiral arms twist into such perfect symmetry, or will the chaos leave something entirely different? The whirlpool doesn't just show us how galaxies evolve, it reminds us that even in the vastness of space, nothing exists in isolation. Every majestic spiral, every blazing star cluster is part of a larger story, one written in gravity, gas, and time. Few cosmic collisions are as striking or as strangely beautiful as the Medusa merger. Officially known as NGC 4194, this chaotic dance of galaxies sprawls across 130 million light-years, resembling a celestial jellyfish with tentacles of stars stretching into the void. At its heart, two spiral galaxies have slammed together with such force. They've birthed a spectacle of destruction and rebirth, their once orderly structures shredded into a swirling tempest of light. But the real showstopper is that 300,000 light-year-long tidal tail, a river of orphaned stars and gas flung into space like glitter from a spinning top. This isn't just a crash, it's a cosmic recycling plant where the raw materials of old galaxies are being forged into something new. What makes the Medusa merger so mesmerizing isn't just its scale, it's the physics at play. As the galaxies grazed each other, their mutual gravity stretched their spiral arms like taffy, ejecting billions of stars into that colossal tail. Yet unlike the scattered debris of most collisions, this tail is densely packed with hydrogen gas, the lifeblood of star formation. And here's where it gets wild. That gas isn't just drifting away. It's collapsing under its own gravity, forming pockets so dense they ignite into newborn stars outside the galaxies themselves. Imagine two painters flinging their brushes, only for the splattered paint to arrange itself into new masterpieces midair. That's the level of chaos and creativity we're witnessing here. Astronomers call these rogue stellar nurseries tidal dwarf galaxies, miniature galaxies born from the wreckage of larger ones. The Medusa's tail boasts several, each a snapshot of how the universe repurposes chaos into creation. But the real surprise, these dwarfs aren't just temporary flickers. Some contain enough gas and dark matter to survive for billions of years, potentially becoming permanent fixtures in the cosmic web. It's a revelation. Galactic mergers don't just destroy, they seed the universe with new structures, scattering future galaxies like dandelion fluff across the void. Yet the Medusa's secrets go deeper. Infrared observations reveal its core is a riot of star birth, with clusters forming at a rate 10 times faster than in the Milky Way. All that colliding gas has triggered a starburst frenzy, lighting up the galactic center like a firework. But there's a twist despite the violence. The supermassive black holes at the hearts of the original spirals haven't yet merged. Instead, they orbit each other in a deadly waltz, their gravitational waves humming a tune we might detect with future telescopes. When they finally collide, the resulting quasar could outshine the entire remnant galaxy, a final act in this cosmic drama. The Medusa merger is more than a spectacle, it's a time machine. By studying its tidal tail, scientists can trace how gas behaves during collisions, key to understanding why some merged galaxies become ellipticals, while others, like the whirlpool, retain their spirals. And those tidal dwarfs, they might solve a long-standing puzzle: how small galaxies form in a universe dominated by giants. Every tendril of this cosmic jellyfish holds clues, reminding us that even in destruction, the universe is always building. After all, in another 4 billion years, when the Milky Way meets Andromeda, we'll be starring in a show just like this one, only with front-row seats to the chaos. The Black Eye Galaxy doesn't just look sinister, it behaves like something out of a cosmic horror story. Officially catalogued as M64, this spiral galaxy spins 40 million light-years away in the constellation Coma Berenices, its haunting appearance dominated by a thick, ink-eyed dust lane that wraps around its core like a bruised eyelid. But the real terror lies beneath its ghostly glow. This galaxy isn't just rotating, it's tearing itself apart. While most galaxies spin as a single, cohesive disk, M64's inner and outer regions whirl in opposite directions, a cosmic contradiction so bizarre it can only mean one thing. This galaxy is the product of a violent, ancient collision, and its scars never fully healed. At first glance, the Black Eye seems ordinary, a tilted spiral with a prominent dust lane, not unlike our own Milky Way. But in the late 1990s, astronomers noticed something unsettling. The galaxy's inner 3,000 light-years rotate clockwise, while everything outside that boundary spins counterclockwise, like two interlocked gears grinding against each other. This isn't just unusual, it's unprecedented in an otherwise well-ordered spiral galaxy. The culprit, a long-ago merger with a smaller satellite galaxy, one that struck at such a steep angle. It sent shockwaves through M64's gas and stars, reversing the outer disk's spin like a cosmic slap. Evidence of this cataclysm lingers in the galaxy's chaotic structure. The thick dust lane blocking starlight, that's the debris from the collision, a swirling storm of gas and soot still settling from the impact. And nestled within it are pockets of frenzied star birth, where compressed gas ignites into blue-hot clusters, cosmic fireworks triggered by the gravitational turmoil. It's as if the galaxy's outer regions are still reeling from the hit, their motion locked in a perpetual tug of war with the inner core. But here's the twist: the Black Eye's opposing spins should have triggered a catastrophic collapse by now, with gas clouds slamming into each other and collapsing into waves of supernova. Instead, M64 thrives, its opposing rotations somehow coexisting. The secret might lie in dark matter. Simulations suggest the original galaxy's halo of invisible matter could have acted like a gravitational cushion, absorbing the collision's energy and preventing total chaos. Think of it like dropping a pebble into a bowl of jelly. The outer layers wobble wildly, but the center stays eerily still. Yet even this explanation doesn't fully account for the galaxy's eerie stability. Some researchers propose the smaller galaxy didn't just hit M64, it grazed it, transferring enough angular momentum to flip the outer disk without fully disrupting it. Others speculate the collision happened billions of years ago, giving the galaxy time to settle into its strange equilibrium. Either way, the black eye stands as a cosmic oddity, a reminder that even the most serene-looking galaxies can hide violent pasts, and that the universe has a flair for turning chaos into hauntingly beautiful contradictions. What makes this discovery even more compelling is its rarity. Of the billions of galaxies we've observed, only a handful exhibit this kind of counter-rotation, and none as dramatically as M64. It's a living laboratory for studying how mergers shape galactic evolution, proving that sometimes the most revealing cosmic stories aren't written in starlight but in the silent, stubborn defiance of dust and dark matter. The Cartwheel Galaxy doesn't just spin, it ripples. Floating 500 million light-years away in the constellation Sculptor, this cosmic bull's-eye looks like someone dropped a rock into a galactic pond, sending concentric rings of starlight pulsing outward. But this isn't the work of gentle forces, it's the aftermath of one of the most violent collisions in the universe, a head-on smash so powerful, it reshaped an entire galaxy in an instant. What makes the Cartwheel so mesmerizing isn't just its shape, it's the sheer violence of its creation. Roughly 200 million years ago, a blink in cosmic time, a smaller galaxy speared through its heart at nearly 2 million miles per hour. The impact sent shockwaves racing through the Cartwheel's gas clouds, compressing them into dense, luminous rings. Like a stone tossed into water, the collision created waves, except these ripples are 30,000 light-years apart, each one a breeding ground for millions of new stars. Hubble's ultraviolet images reveal the proof: clusters of young, blue stars lighting up the rings like neon signs, their birth fueled by the chaos. Simulations of the crash paint an even wilder picture. As the intruder galaxy plowed through, it didn't just disturb the Cartwheel's gas, it splashed it outward. The galaxy's outer arms, once a neat spiral, stretched into a fragmented halo, while the core rebounded like a compressed spring, creating that distinctive bullseye. But here's the twist: the intruder didn't stick around. It sailed right through, leaving the Cartwheel to deal with the wreckage, a celestial hit, and run frozen in time. What's truly astonishing is the speed of the transformation. Galactic collisions usually take billions of years to unfold, but the Cartwheel's rings formed in a cosmic heartbeat. That's because the shockwaves moved faster than the galaxy's rotation, effectively overtaking its natural structure. It's like throwing a bowling ball into a spinning pizza dough. The dough doesn't just warp, it splatters into a shape dictated by the impact, not its original motion. Yet for all the destruction, the Cartwheel isn't dying, it's reinventing itself. Those star-studded rings are proof. As gas piles up along the shock fronts, it ignites into stellar nurseries, birthing stars at a rate 10 times faster than the Milky Way. Some of these clusters are so massive, they'll likely outlive the galaxy itself, drifting into space as future globular clusters. The Cartwheel's story isn't just about destruction, it's about resilience. Even as the galaxy's original structure unravels, new patterns emerge, proving that chaos and creation are two sides of the same cosmic coin. And somewhere out there, the intruder galaxy sails on, its gravity still tugging at the Cartwheel stars, a ghostly reminder that in the universe, no collision is ever truly over. The Tadpole Galaxy isn't just escaping a collision, it's painting with its own destruction. Floating 420 million light-years away in Draco, this distorted spiral trails a 280,000 light-year long tail of stars and gas, a shimmering scar left by a gravitational assault so brutal it ripped the galaxy's spiral arms clean off. But this isn't just debris, it's a stellar nursery in exile, a river of orphaned star clusters drifting through the void, each one a glittering time capsule from the moment of impact. The violence began roughly 100 million years ago, when a smaller intruder galaxy plowed through the tadpole's disk like a bullet through smoke. The tidal forces stretched the larger galaxy's outer layers into that colossal tail, flinging billions of tons of gas and stars into intergalactic space. Yet instead of scattering randomly, the ejected material did something astonishing. It coalesced. Gravity worked its magic, compressing pockets of gas into dense knots that ignited into blue hot star clusters, each one a miniature galaxy in its own right. These aren't just survivors of chaos, they're products of it, cosmic phoenixes born from the wreckage. What's truly baffling is the tail's longevity. Most tidal tails dissolve over time, their stars diffusing into the darkness, but the tadpole's tail is thriving with over 1,000 confirmed star clusters, some as massive as the largest in our Milky Way. Infrared observations reveal why. The tail is denser than predicted, packed with enough hydrogen gas to keep forming stars for billions of years. It's as if the galaxy's lifeblood was siphoned into this celestial tributary, creating a self-sustaining chain of stellar nurseries far from their parent galaxy. This challenges everything we thought we knew about where stars can form. Conventional wisdom says galaxies are the universe's star factories, their dense cores and spiral arms ideal for birthing suns. But the tadpole's tail proves the opposite. Stars can ignite anywhere, even in the abyss between galaxies if conditions are right. Some of these rogue clusters might even survive long enough to become free-floating dwarf galaxies untethered to any parent. Imagine entire civilizations could one day rise in these exiled clusters, their night skies dominated not by a spiral galaxy's glow, but by the faint, fading streak of the tail that birthed them. The tadpole's story isn't just about destruction, it's about legacy. Every cluster in that tail is a fossilized snapshot of the collision, their ages and compositions revealing the precise moment they were torn loose. By studying them, astronomers can reconstruct the crash like forensic detectives, piecing together the intruder's speed, angle, even its mass. And perhaps most intriguingly, the tail hints at a universal truth: galaxies aren't static islands. They're dynamic, messy beings, constantly shedding material into the void where it might just seed the next generation of stars. So while the tadpole galaxy's misshapen form will eventually settle into a quiet elliptical, its tail will live on, a glittering testament to the universe's unyielding creativity. After all, in the grand cosmic ballet, even chaos has a way of writing poetry. The antennae galaxies aren't just colliding, they're tearing each other apart in a celestial spectacle that makes even the most dramatic cosmic crashes look tame. Officially catalogued as NGC 4038 and NGC 4039, this entangled pair floats 60 million light-years away, their once pristine spiral arms now twisted into colossal streams of stars and gas stretching hundreds of thousands of light-years into space. These aren't just random debris, they're the galaxy equivalent of battle scars, evidence of a gravitational tug of war that's been raging for over 300 million years. And right now, we're witnessing the climax, a fireworks show of star birth so intense, it's devouring the galaxy's remaining fuel at a breakneck pace. What makes the antennae so mesmerizing isn't just the chaos, it's the stakes. Galactic mergers usually happen in slow motion, but here, the violence is unfolding in real time. As the two spirals locked in their death spiral, their mutual gravity ripped apart their delicate structures, compressing vast clouds of hydrogen gas into dense knots. The result, a starburst frenzy, with new stars igniting at a rate 100 times faster than our Milky Way. Hubble's images reveal the proof: over 1,000 brilliant blue star clusters, each one packing the luminosity of 1,000,000 suns, lighting up the wreckage like flares in a storm. But this frenzy comes at a cost. All that star formation is burning through the galaxy's gas reserves like wildfire, and once it's gone, there's no getting it back. Current estimates suggest the antennae have already expelled half their original gas into intergalactic space, a loss equivalent to 10 billion suns worth of material. Some of it is being blown away by the sheer force of supernova, the explosions of massive stars carving bubbles in the wreckage. The rest is being stretched into those iconic tidal tails, the very features that give the antennae their name. These tails aren't just decorative, they're highways of exile, ferrying gas and stars into the void where they'll never return. Yet even as the galaxies bleed their lifeblood into space, something extraordinary is happening. Deep in their tangled cores, the supermassive black holes won from each original spiral are circling each other in a lethal dance. Right now, they're about 3,000 light-years apart, close enough to warp the surrounding gas into glowing spirals but still too distant to merge. When they finally collide, the resulting gravitational waves will shake the fabric of spacetime itself. That moment might be tens of millions of years away, but when it comes, it'll release more energy than all the stars in the observable universe combined. The antennae's fate is already sealed. In another billion years, the merger will be complete, leaving behind a single, featureless elliptical galaxy, a quiet tombstone for the spirals that once were. The tidal tails will fade, their exiled stars drifting into darkness, but for now, this cosmic wrecking ball is a living laboratory, proving that even in destruction, the universe finds a way to create. Every newborn star cluster, every shockwave rippling through the gas, is a reminder that chaos and beauty aren't opposites, they're two sides of the same cosmic coin. And somewhere in that maelstrom, the raw materials for future planets, and perhaps life itself, are being forged in the fires of a galaxy's messy divorce. The mice galaxies aren't just colliding, they're performing an almost balletic display of gravitational choreography, their twin tails stretching 500,000 light-years behind them like cosmic ribbons frozen mid-twirl. Officially known as NGC 4676 and NGC 4676a, this pair of spiral galaxies lies 300 million light-years away in the constellation Coma Berenices, locked in a slow-motion dance that's reshaping them before our eyes. What makes this encounter so mesmerizing isn't the chaos, it's the eerie symmetry, as if the universe itself paused to ensure each galaxy's destruction unfolded in perfect mirror image. Unlike the violent head-on smash that created the Cartwheel Galaxy, the mice are engaged in a grazing collision, their disks brushing past one another at a shallow angle like two ships passing in the night. This gentle approach is why their spiral arms haven't shattered into randomness. Instead, their mutual gravity has orchestrated an elaborate tidal tug of war, pulling stars and gas from each galaxy's near side while flinging material from the far side into those iconic tails. The result, two near-identical arcs of orphan stars, each a testament to gravity's precision even in destruction. But here's the twist, those tails aren't just debris, they're time capsules. Because tidal forces pull material outward at different speeds depending on its distance from the galactic core, the tails act like cosmic sorting machines. Older, redder stars which orbit closer to the center get stretched into the tail's innermost regions, while younger, bluer stars and gas clouds are flung farther out. By studying these gradients, astronomers can essentially rewind the collision, reconstructing the galaxy's original shapes and trajectories like forensic scientists analyzing skid marks. What's truly astonishing is how intact the mice remain despite the turmoil. Their cores still separate and glowing brightly, have resisted merging, a reminder that galactic collisions aren't instant events but processes spanning hundreds of millions of years. The gas clouds in their disks, though distorted, continue churning out new stars, just at a more frantic pace than before. It's as if the galaxies are resisting their own dissolution, clinging to their identities even as they're pulled apart. This delicate balance reveals a universal truth: galaxies are tougher than they look. Their vast collections of stars, gas, and dark matter create gravitational glue that holds them together even under extreme stress. The mice's long tails might look like evidence of impending doom, but they're really proof of resilience, a phase in a galactic life cycle that's as natural as it is spectacular. And somewhere in the distant future, when the cores finally merge, the mice will become something new, a single elliptical galaxy, its once elegant spirals erased but its story preserved in those shimmering tidal tails. Until then, they remain a masterclass in cosmic dynamics, proving that even in chaos, there's an underlying order, a rhythm to the universe that turns destruction into art. Mayall's object isn't just another galaxy, it's a cosmic crime scene. Floating 500 million light-years away in the constellation Ursa Major, this bizarre, question-mark-shaped structure looks like someone took a shotgun to the night sky and left a gaping hole through a galaxy's heart. Officially catalogued as ARP 148, this twisted wreckage has sparked decades of debate. Did a high-speed intergalactic projectile punch straight through it, or are we witnessing the aftermath of a collision so weird it defies every simulation? The bullet hole theory is the most tantalizing. If you look closely at Mayall's object, you'll spot a near-perfect tunnel carved through its center, a corridor of darkness where stars and gas should be but aren't. Surrounding this void, the galaxy's remaining material flares outward in a chaotic splash pattern, like ripples from a stone tossed into a pond. Some astronomers argue this could be evidence of a rare, dark galaxy, a clump of rogue dark matter that barreled through at millions of miles per hour, its gravity acting like a cosmic plow, clearing everything in its path. Imagine swinging a sledgehammer through a cloud of glitter. The hammer leaves no trace, but the glitter sprays in its wake. That's essentially what might have happened here, only the hammer was an invisible mass and the glitter was an entire galaxy's worth of stars. But there's a competing explanation, one just as strange. Instead of a single, catastrophic impact, Mayall's object could be the mangled remains of two galaxies that collided in a freakishly precise way. Simulations suggest that if one spiral galaxy sideswiped another at just the right angle, their combined gravity could warp the survivor into this twisted question-mark shape, with the hole being a temporary gap where their cores missed each other entirely. The trailing arcs of stars and gas, those would be tidal tails stretched like taffy during the near miss. It's like watching two cars graze each other on a highway, their paint swapping but their frames remaining intact, except in this case, the paint is entire star clusters and the highway is the void of space. What makes this mystery so compelling is the evidence on both sides. Proponents of the bullet theory point to the eerie cleanliness of that central tunnel, too straight, too empty for a typical merger. They argue that if another galaxy had caused this damage, we'd see debris, shockwaves, or at least some residual starlight in the gap. Instead, it's as if something invisible and unimaginably dense bulldozed through, leaving no trace except the destruction in its wake. Yet merger theorists counter with the galaxy's overall symmetry. The twin arcs curling away from the center are textbook tidal features, identical to those seen in other galactic collisions. And the hole might not be empty. Recent radio observations detected faint streams of hydrogen gas crisscrossing the void, suggesting the gap is more like a temporary wound, already healing as gravity pulls displaced material back in. The truth might lie somewhere in between. Some researchers speculate Mayall's object could be a two-act tragedy. First, a near-miss collision warped the galaxy into this odd shape. Then a dark matter subbelow, a smaller, invisible clump, punched through the weakened center, widening the gap. If so, it'd be a cosmic coincidence of almost impossible odds, like lightning striking the same tree twice during a hurricane. What's undeniable is that Mayall's object forces us to rethink how galaxies interact. Most mergers are messy, chaotic affairs, but this one, whether by impact or near miss, showcases an unnerving precision, as if the universe itself paused to carve a question mark into the cosmos. And that's the real lesson here. Sometimes the most profound discoveries aren't answers. They're mysteries hanging in the void, daring us to look closer. Hanni's Vorwerp isn't just a cosmic oddity, it's a ghost story written in light. Floating near the spiral galaxy IC 2497, this eerie, glowing green cloud stretches tens of thousands of light years, its ethereal glow defying explanation. When Dutch schoolteacher Hanny van Arkel spotted it in 2007 while classifying galaxies for the Galaxy Zoo project, astronomers were stunned. Here was a celestial object unlike anything they'd seen before, a vast, isolated cloud of ionized gas, blazing with the intensity of a quasar but with no visible energy source to power it. The answer to this mystery didn't just rewrite the rules of galactic behavior, it revealed a universe where even the quietest galaxies hide violent pasts. The secret lies in the Voorwerp's unnatural color. That vivid green hue comes from oxygen atoms stripped of their electrons, a process that requires an immense flood of ultraviolet radiation. Normally, gas only glows this intensely near active galactic nuclei, the superheated regions around feeding supermassive black holes. But IC2497's core is eerily quiet, its black hole dormant. So how did this cloud light up? The answer is as haunting as it is brilliant. We're witnessing a light echo from a cataclysm that occurred tens of thousands of years ago. Here's what likely happened. Roughly 100,000 years before Hanny spotted the Voorwerp, IC2497's black hole went on a feeding frenzy, briefly transforming into a quasar, a beacon of radiation so powerful it outshone the entire galaxy. The outburst ionized surrounding gas clouds, including the one we now call the Voorwerp, charging them like a neon sign. But by the time the light reached Earth, the quasar had already shut off, leaving the Voorwerp as the only visible relic of that violent episode. It's the cosmic equivalent of walking into a room just as someone turns off a flashlight. The afterimage lingers, but the source is gone. What makes this discovery revolutionary isn't just the Voorwerp itself, it's what it implies about galactic black holes. Astronomers once assumed quasars were rare, fleeting events, but the Voorwerp suggests even quiet galaxies like IC2497 have explosive pasts, their black holes cycling through periods of activity and dormancy. This means the universe could be littered with similar ghostly clouds, faint echoes of ancient outbursts waiting to be discovered. In fact, follow-up surveys have since identified dozens of these Voorwerps, little Voorwerps in Dutch, each one a fossilized snapshot of a black hole's tantrum. The irony is delicious. These glowing clouds, born from some of the most destructive forces in the universe, are now helping scientists piece together galactic histories that would otherwise be lost to time. By measuring their size, shape, and ionization levels, astronomers can reconstruct the intensity and duration of long-dead quasars, essentially carbon-dating black hole activity. The Voorwerps aren't just cosmic ghosts, they are forensic evidence revealing that even the sleepiest galaxies might be hiding explosive secrets beneath their calm exteriors. And that's the real lesson here. The universe doesn't just erase its past, it leaves clues, glowing green signposts in the void, waiting for sharp-eyed observers like Hanny van Arkel to stumble upon them. Who knows how many other cosmic mysteries are hiding in plain sight, just one curious glance away from rewriting everything we thought we knew. Stretching across the night sky like a celestial scar, the Magellanic Stream is one of the most enigmatic structures in our galactic neighborhood, a river of gas 600,000 light-years long, arcing behind the small and large Magellanic Clouds as they orbit the Milky Way. For decades, astronomers assumed this faint ribbon was simply debris, the cosmic equivalent of breadcrumbs left by two dwarf galaxies as they drifted through space. But the truth is far stranger, forcing us to rethink how even the smallest galaxies can shape and be shaped by the giants they orbit. The mystery begins with the stream's sheer scale. If you could see it with the naked eye, it would span 20 times the width of the full moon, a gossamer trail of hydrogen gas so vast it defies simple explanations. Early observations suggested it formed through tidal stripping, the Milky Way's gravity wrenching gas away from the Magellanic Clouds as they swung past. It's a common process. Galaxies often steal material from one another in close encounters. But there's a problem. The stream's gas isn't just from the clouds. Spectroscopic analysis reveals some of it matches the composition of the Milky Way's own halo, the diffuse sphere of gas enveloping our galaxy. This raises a tantalizing possibility. The stream might not just be losing material, it could be gaining it, with the Milky Way's halo gas actively sculpting its structure. Imagine the scene. As the Magellanic Clouds orbit, they don't move through empty space, they plow through the Milky Way's extended atmosphere, a thin but pervasive sea of hot gas. This creates a dynamic pressure like a boat's bow wave, stripping gas from the clouds while simultaneously compressing and heating the Milky Way's own halo material. The result is a hybrid structure, part tidal tail, part galactic wake, woven together by forces we're only beginning to map. Recent simulations show this interplay could explain the stream's intricate filaments, where pockets of cooler, denser gas from the clouds mix with ionized plasma from the halo, creating a tapestry of temperatures and densities unlike anything else in the local universe. Yet for all the progress, the stream still holds puzzles. Its northern reaches curl toward the Milky Way, while the southern end stretches away, as if caught in a cosmic tug of war. Some researchers argue this bifurcation points to an ancient collision between the two Magellanic Clouds long before they fell into our galaxy's grasp, a violent encounter that pre-stretched their gas, making it easier for tidal forces to later pull it into the stream. Others propose the Milky Way's magnetic fields are playing a role, channeling the gas into these distinct strands like invisible rails. What's clear is that the Magellanic Stream isn't just a fossil of past interactions. It's a live experiment, a real-time demonstration of how galaxies evolve through both theft and collaboration. As new telescopes like the SKA and James Webb peer deeper into its structure, they're not just tracing the history of three galaxies, they're revealing the invisible forces that bind them, proving even the faintest threads in the cosmos can hold the weight of cosmic revelation. The Leo Ring defies the universe's usual chaos. It's a silent, sprawling ribbon of hydrogen gas stretching 650,000 light-years across, drifting untouched between galaxies like a relic frozen in time. Unlike most cosmic structures which blaze with newborn stars or bear the scars of collisions, this primordial cloud remains eerily pristine, its gas unpolluted by the alchemy of star formation. It's as if we've stumbled upon a cosmic fossil, a surviving whisper from an era when the universe was still assembling its first galaxies. What makes the Leo Ring so extraordinary isn't just its size, it's its purity. Composed almost entirely of hydrogen and helium, the same raw materials that filled the cosmos after the Big Bang, this vast torus of gas floats in near-perfect isolation. No stars glitter within it, no supernova have enriched it with heavier elements. It's a time capsule offering a glimpse of the universe before metals, before light, before even the first stars flickered to life. The question is, how did something this fragile survive 13 billion years without collapsing into galaxies or being shredded by gravity? One theory suggests the ring is a failed galaxy, a pocket of primordial gas that never quite gathered enough density to ignite star formation. Imagine a cloud of dust hovering in a sunbeam, never coalescing into raindrops. Alternatively, it might be the debris from a near-miss collision between two ancient galaxies, their gravitational tug of war stretching a bridge of gas so thin it couldn't fragment into stars. Radio telescopes have even detected faint echoes of this possible encounter. The galaxies NGC 3384 and NGC 3389 drifting near the ring's edges like guilty parties fleeing the scene. But the most tantalizing possibility, the Leo Ring could be a rare survivor from the cosmic web, the filamentary network of gas that fed the universe's first galaxies. Simulations of the early universe show vast rivers of hydrogen flowing along these filaments, funneling material into growing galactic hubs. Most of these streams were absorbed or evaporated eons ago. Yet somehow this one slipped through the cracks, a solitary thread left dangling in the dark. The mystery deepens when you consider the ring's stability. Left alone, a gas cloud this massive should have collapsed under its own gravity eons ago. The fact that it hasn't hints at invisible forces at work, perhaps a halo of dark matter cradling the gas, or magnetic fields weaving through it like an invisible scaffold. Some researchers even speculate the ring might be primed for star formation, its gas teetering on the edge of ignition. If so, we could be witnessing the prelude to a celestial fireworks show, one delayed by billions of years. For now, the Leo ring remains a paradox, a structure so simple it defies explanation. It challenges our assumptions about how galaxies form and evolve, reminding us that the universe often preserves its oldest secrets in plain sight. And as telescopes peer deeper into its delicate structure, they're not just studying a cloud of gas, they're reading a love letter from the cosmos itself, written in the language of hydrogen and time. The Virgo cluster should be teeming with dwarf galaxies, hundreds, maybe even thousands of them. That's what our best simulations predict. Yet when astronomers peer into this nearby galactic metropolis, just 55 million light-years away, they find a puzzling emptiness. Where theory says there should be a bustling crowd of tiny galaxies, there's, well, less, far less. It's like showing up to a party expecting a packed room, only to find a handful of guests milling around. So what happened to all the missing dwarfs? The answer might rewrite our understanding of how galaxies live and die in the universe's densest neighborhoods. First, let's talk about expectations. In the modern cosmic web, dwarf galaxies are supposed to be everywhere. They're the universe's building blocks, the leftover scraps from the mergers that built giants like the Milky Way. Current models rooted in dark matter theory suggest clusters like Virgo, a gravitational hub with over 2,000 known galaxies, should be swarming with them. Their halos of invisible dark matter act like celestial glue, trapping gas and stars into these small, durable structures. Yet Virgo's dwarf count falls drastically short. Some estimates put the deficit at 70% or more. That's not just a rounding error, it's a cosmic crisis. One possibility is as brutal as it is elegant. Virgo ate them. Clusters are galactic slaughterhouses where the immense gravity of the central giants, like the supermassive M87, rips apart smaller neighbors. As dwarfs plunge into the cluster's core, they're stripped of gas, stretched into streams, and eventually digested. The evidence is etched across Virgo in tidal dwarfs, a faint, mangled remnants of galaxies caught mid-destruction. But here's the catch: tidal destruction can't explain the scale of the missing dwarfs. There simply hasn't been enough time since the cluster formed to dissolve that many galaxies. That's where dark matter tweaks enter the picture. If dark matter behaves differently in clusters than in simulations, say, if it's warmer or more diffuse, it might fail to anchor dwarf galaxies effectively. Without that scaffolding, dwarfs could evaporate before they ever fully form, like sandcastles crumbling at high tide. Some theorists even propose dark matter might interact with itself, annihilating or scattering in ways that leave fewer dwarf-sized halos intact. It's a radical idea, but one that could solve multiple cosmic mysteries at once. Yet there's another, more provocative explanation: the Milky Way's past. Our galaxy might have once been part of a larger group that collided with Virgo eons ago, a cosmic smash and grab that stole away dwarfs in the chaos. Traces of this encounter could linger in the Milky Way's outer halo, where oddball stars and clusters move in suspiciously Virgo-like orbits. If true, it'd mean the missing dwarfs aren't missing at all. They're hiding in plain sight, kidnapped by our own galaxy. The truth likely blends all three scenarios. Virgo's dwarf deficit isn't just a counting problem, it's a window into the messy, violent processes shaping galactic ecosystems. Every absent galaxy whispers a story of dark matter's secrets, of clusters' appetites, or of ancient thefts written in starlight. And as telescopes like Vera Rubin and James Webb turn their gaze toward Virgo, they're not just hunting for dwarfs. They're uncovering the rules of cosmic survival, and proving that even emptiness can be full of answers. The Bullet Cluster isn't just a cosmic collision, it's a smoking gun. When astronomers first studied this clashing pair of galaxy clusters 200 million light-years away, they weren't just witnessing chaos, they were staring at proof of something invisible shaping the universe itself. Here, in the wreckage of one of the most violent encounters in the cosmos, dark matter, the elusive substance that makes up 85% of the universe's mass finally revealed its hand, not by what was seen, but by what wasn't. At first glance, the Bullet Cluster looks like a train wreck in slow motion. Two galaxy clusters, each weighing a quadrillion suns, have plowed through each other at millions of miles per hour, stripping gas and stars apart in a spectacle of raw physics. X-ray telescopes capture the aftermath, a searing cloud of superheated plasma, twisted into a bullet-like shape by the impact. But the real story lies in what didn't collide: the vast majority of the cluster's mass, which sailed through the crash untouched. This is where gravitational lensing comes in. Einstein predicted that massive objects warp space-time, bending light like a lens. By mapping how the Bullet Cluster distorts light from background galaxies, astronomers could trace its true mass distribution. The result was staggering. The visible gas, the only part of the clusters that actually collided, accounted for just 15% of the total mass. The rest, an invisible halo of something, had passed right through the collision, dragging the galaxies along with it. That something could only be dark matter, its gravity gripping the stars while the ordinary gas lagged behind like cosmic exhaust. The implications were earth-shaking. For decades, dark matter had been a theoretical necessity, a placeholder to explain why galaxies didn't fly apart given their visible mass. But here was direct evidence. Dark matter wasn't just a mathematical trick. It was real, it was separate from normal matter, and it dominated the universe's structure. The Bullet Cluster became the first laboratory where dark matter's effects were seen, not inferred. Yet the discovery raised new questions. Why did dark matter interact so weakly with itself and ordinary matter? Simulations suggested it should form dense clumps, yet the Bullet Cluster's dark halos remained smooth, as if immune to friction. Some theorists wondered if dark matter had hidden properties, self-interacting forces, or even exotic quantum behaviors. Others saw hints of modified gravity theories crumbling under the weight of evidence. What's undeniable is this: the Bullet Cluster didn't just prove dark matter exists. It showed us how it exists as a ghostly scaffold, holding galaxies together even as the visible universe burns and crashes around it. And as we stare deeper into this cosmic collision, we're left with a humbling thought: the universe isn't just stranger than we imagined. It's stranger than we can imagine, with every answer peeling back another layer of mystery. There's something out there, something massive, invisible, and unstoppable, dragging entire galaxies toward it at incomprehensible speeds. Meet the Great Attractor, a gravitational anomaly so powerful, it's compelling thousands of galaxies, including our own Milky Way, to march toward a point in space near the Norma cluster, 500 million light-years away. This isn't just a pull, it's a cosmic current, a river of galaxies flowing toward a hidden destination we still struggle to see, and the reason we can't see it: it's hiding behind the Milky Way's own stars, dust and gas, a region astronomers call the zone of avoidance, where our galaxy's thick disk blocks our view like a cosmic curtain. The Great Attractor was first discovered in the 1970s when astronomers noticed something odd. Galaxies in our local universe weren't just drifting randomly. They were moving together as if swept up in some vast, invisible tide. Measurements showed this flow extended far beyond the Milky Way's immediate neighbors. Galaxies hundreds of millions of light-years away were caught in the same current, all rushing toward a mysterious focal point in the constellation Norma. The sheer scale of this motion defied explanation. Whatever was pulling them had to be unimaginably massive, with the gravitational heft of tens of thousands of Milky Ways combined. Yet when telescopes turned toward that patch of sky, they found nothing obvious, just the Norma cluster, a dense gathering of galaxies impressive in its own right, but nowhere near massive enough to account for the observed pull. That's when the mystery deepened. The Great Attractor wasn't just a single cluster, it was part of something far larger. Behind the zone of avoidance lies the Laniakea supercluster, a web of galaxies spanning 500 million light-years, with the Great Attractor acting as its gravitational heart. Laniakea, Hawaiian for immeasurable heaven, redefined our place in the cosmos, showing that the Milky Way isn't just floating aimlessly, but is part of a sprawling supercluster being drawn toward this hidden epicenter. But even Laniakea's combined mass can't fully explain the Great Attractor's pull. There must be something else lurking behind the curtain, something even more colossal tugging at the strings. Peering through the zone of avoidance is like trying to read a road sign through a blizzard. Visible light gets absorbed or scattered by interstellar dust, but astronomers have workarounds. Infrared and radio telescopes like NASA WISE and South Africa's Mercator can pierce the veil, revealing glimpses of structures previously obscured. These observations have uncovered tantalizing clues: galaxy clusters, filaments of dark matter, and even hints of an enormous concentration of mass nicknamed the Vela supercluster, which might contribute to the attractor's grip. But the puzzle isn't solved yet. Every new observation adds pieces, but the full picture remains frustratingly blurry. One leading theory suggests the Great Attractor isn't a single object but a confluence of multiple massive structures, superclusters, dark matter halos, and perhaps even larger-scale flows we haven't mapped yet. It's like standing near a waterfall and feeling the pull of the water. You're not just reacting to the drop in front of you, but to the entire river system feeding it. Similarly, the attractor might be the focal point of a vast cosmic watershed, where gravitational currents from across the universe converge. What's at stake isn't just understanding this one anomaly, it's decoding the blueprint of the universe itself. The Great Attractor challenges our models of cosmic structure, forcing us to ask, are we missing something fundamental about gravity? Is there more dark matter clustered here than we thought? Or is this a sign of even larger structures beyond our current vision, waiting to be discovered? As telescopes grow more advanced, the zone of avoidance is slowly lifting. Each breakthrough peels back another layer, bringing us closer to unraveling the attractor's true nature. Until then, it remains one of the universe's most humbling reminders. Even as we map the cosmos, some forces still loom in the shadows, pulling the strings behind the scenes. And perhaps that's the most thrilling part, not just the answers we find, but the questions that keep us looking up, wondering what else is out there just beyond our sight. These galactic enigmas aren't just cosmic curiosities, they're stress tests for the fundamental theories underpinning modern cosmology. Take the Hercules-Corona Borealis Great Wall and the giant arc. Their sheer size contradicts the cosmological principle, the bedrock assumption that the universe should look roughly uniform on large scales. If structures this colossal exist, did inflation, the rapid expansion of the early universe, stretch irregularities far beyond what models predict, or does dark matter clump in ways we've yet to comprehend? The answer could rewrite our understanding of cosmic architecture, forcing us to consider whether the universe is more anisotropic, more lumpy than we ever imagined. Dark matter's role is equally under scrutiny. The Bullet cluster famously proved dark matter's existence by showing it could decouple from visible matter during collisions. But the Virgo cluster's missing dwarfs and the counter-rotating chaos of the Black Eye galaxy suggest dark matter might behave in stranger ways than simulations predict. Could it interact with itself through unknown forces or cluster differently in high-density environments? The way dark matter anchors galaxies seems almost too perfect in some cases, too absent in others, a paradox that hints at gaps in our models. Even the Magellanic Stream's intricate filaments, shaped by an invisible tug of war between galaxies, suggest dark matter's influence is subtler and more dynamic than we've assumed. Then there's the problem of timing. The Phoenix Cluster's runaway star formation and the cartwheel galaxies near instantaneous rings defy the slow, gradual evolution we expect from galactic interactions. If mergers can trigger starbursts or reshape entire galaxies in mere millions of years, a blink in cosmic terms, our simulations might be missing key physics like turbulent gas dynamics or magnetic fields on galactic scales. Similarly, Hoag's object and the Red Rectangle Nebula challenge assumptions about how long delicate structures can persist without dissipating. Their unnatural symmetry implies hidden stabilization mechanisms, perhaps involving dark matter or yet undetected gravitational resonances. The upcoming generation of telescopes like JWST and the Vera Rubin Observatory promises to peel back these layers. JWST infrared eyes could reveal the faintest tidal dwarf galaxies in the tadpole's tail, testing theories of star formation in exile. Rubin's all-sky surveys might uncover more impossible ringed galaxies or voids, mapping the universe's true heterogeneity. And as gravitational wave detectors grow more sensitive, they could catch the faint ripples from mergers like the antennae galaxies, offering a live look at how black holes coalesce. What's at stake isn't just tweaking equations, it's recognizing that the universe thrives on exceptions. From the great attractor's hidden pull to the Fermi bubble's violent origins, each anomaly whispers a tantalizing truth. Our models are approximations, not blueprints. The cosmos delights in bending rules, and every time we think we've charted its boundaries, it reveals a new frontier. Whether it's rewriting inflation, redefining dark matter, or accepting that galactic evolution is far messier than we thought, one thing is clear. The universe still holds the pen, and we're just beginning to read the story. From the Hercules-Corona Borealis Great Wall, a structure so vast it defies the very notion of cosmic uniformity, to the eerie perfection of Hoag's object, a galaxy that looks more like a celestial bullseye than anything nature should produce, the universe has proven itself an endless well of surprises. These aren't just oddities, they're masterclasses in cosmic creativity, each one stretching the limits of what we thought possible. Take the Bullet Cluster, where dark matter's ghostly fingerprints were finally revealed, or the Red Rectangle Nebula, its geometric precision so flawless it feels engineered. And who could forget the Great Attractor, that invisible force dragging thousands of galaxies toward a mystery hidden behind our own Milky Way's dust. These structures don't just challenge our textbooks, they rewrite them. But here's the thrill, we've barely scratched the surface. Every time we point a telescope at the seemingly empty darkness, it coughs up another enigma. The Fermi bubbles, the Medusa merger's tidal dwarfs, the Leo ring's primordial purity. Each discovery peels back another layer of the universe's playbook, revealing rules we never knew existed. And with tools like JWST and the Vera Rubin Observatory coming online, we're poised to uncover even more. Maybe we'll finally solve the dark flow's multiverse riddle or spot another ringed galaxy that makes Hoag's object look ordinary. Perhaps the key to dark matter is hiding in the Virgo cluster's missing dwarfs, or the next cosmic Great Wall is lurking just beyond our current maps. That's the beauty of space. It's the ultimate detective story with clues scattered across billions of light years. So stay curious. The next time you look up at the night sky, remember, what we see is just the prologue. The real story is still being written in quasars we haven't detected, in collisions we haven't witnessed, in voids that might hide universes beyond our own. And who knows, maybe your favorite cosmic mystery hasn't even been discovered yet. Drop yours in the comments. Is it the haunting symmetry of the Sombrero Galaxy, the Phoenix Cluster star making frenzy, or something even stranger? The universe is listening, and if history's any guide, it's got plenty more surprises up its sleeve.